Hello, AP Physics. You are going to be the guinea pig. You're the first video I'm making. So, we shall see how this goes. This is just going to be an overview of Chapter 15. Stuff we've talked about, although I know the last couple of days you guys kind of spaced out and maybe didn't pay much attention as you should have. But we're going over Chapter 15 so you guys can do a couple homework problems. Let's go for it. So we're still talking about waves, and even in Chapter 16 we're going to be talking about waves. But Chapter 15 kind of laid down a decent amount of information that we'll need to be able to do Chapter 16. And we're spending more time in Chapter 15 than Chapter 14 because 14 laid even like just the basic stuff, and this is like the mid-tier stuff going on. So this question says a wooden toy hangs from a spring. When you pull it down and release, it reaches the highest point of its motion after 1 second. What is the frequency of the oscillation? Well, we know that if it goes from the bottom to the top in 1 second, a full rotation would be from the bottom to the top back to the bottom. So from here to here is 1 second. That means going back is another second. So overall, the period is 2 seconds. We know that frequency is 1 over the period. So 1 over 2 seconds would be, apparently we skip it, would be letter D right here, 0.5 hertz. And then we got a question like this. Which of the following is a longitudinal wave? So remember that when I'm talking right now, I'm sending out waves like this, and they're going out like that. So I send the disturbance that way, and the wave travels that way. That's a longitudinal wave. There's also things called transverse waves, and those are the things to where if I go like this, then the wave travels out like that. So that would be closer to a whip or the water. So when we see this question, which of the following is a longitudinal wave, it's going to be sound wave, because the disturbance is going in the same direction as the actual wave itself. The other ones, it's opposite. If you drop a rock in water, the waves don't go down farther into the pool, they go to the side. They go to the perpendicular to the original disturbance. The same thing with light. That's a little more abstract, but light's going up and down as it moves left and right, so it's not longitudinal. When the particles of a medium move with simple harmonic motion, this means the wave is it's asking for the most generally correct answer, and that would be a sinusoidal wave. Because remember, during a wave, the particles themselves are not moving left and right, they're just going up and down. So if you drop a rock here, and water waves go out that way, this little water particle is just waiting for the wave to get here, and then it goes up and down, and up and down. It doesn't go left or right or anything. So if it goes up and down, and you map that to the left and right, it makes a sinusoidal wave. A 100 hertz sound wave is traveling through the air. If we increase the frequency to 200 hertz, this will do what to the wavelength? Okay, well, you have to remember that the speed is going to stay constant, right? It doesn't matter how high pitch of a noise you make, the noise will still travel through the air at the same speed. So the speed is going to stay the same. We're changing the frequency, and we want to know what's going to happen to the wavelength. And it's going to have to decrease the wavelength. It's going to make the distance between the wavelengths smaller, because there's more waves in a smaller amount of space, essentially, which means all the tops of the waves have to get scrunched together, so the entire wavelength decreases. I don't think we talked about this. A lens collects light and focuses into a small spot. This increases the what of the wavelength, or of the light wave? It does not increase wavelength, frequency, or energy. What it does is increase the intensity. You're taking all the energy and all the light from a wide area and focusing on one spot. So we're not making any more energy. We're not changing the frequency or wavelength. It's still all the same light, but we're moving it all to one single spot, so the intensity increases. We measure sound in decibels. Okay, So that's just overall introduction. Let's go over a couple of things I know we did. We got something like this. When does a spider sense his lunch? All spiders are very sensitive to vibration. An orb spider will sit at the center of its large circular web and monitor radial threads for vibrations created when an insect lands. Assume that these threads are made of silk with a linear density of 1.0 times 10 to the negative fifth kilograms per meters under a tension of 0.40 newtons. Both are typical numbers. If an insect lands in the web 30 centimeters from the spider, how long will it take for the spider to find out? So the moment the insect hits the web, that little wave pulse is going to go, and then the spider is going to be able to feel that. But we don't know how fast that thing is going yet. We don't know how fast the wave itself is. So I encourage you guys to be following along in your book, because like if I reference an equation, like this equation needs 15.2, I'm not going to have 15.2 up on the board, but 15.2 up on the board, up on the whatever this is, up on the screen. But this first thing right here, this is from equation 15.2. We got the speed of the wave equals the tension of the material divided by the linear density of the material. And we were given both of these. In the problem it said these two numbers, it gave these to us. We didn't have to find these out. So we can just find the speed that a wave travels through spider silk by plugging in this stuff, taking the square root, and you get 200 meters per second. That part is the new part of this chapter, and then the time it takes for the wave to travel a distance of 30 centimeters. Well, that's just your old right here, velocity equals distance over time. We just rearrange it, and then we get distance divided by velocity equals 1.5 milliseconds. So that's how long it takes for the spider to actually note. That's how long it takes for the spider to feel that, and then it's going to go over and eat the bug or whatever. I remember we did this problem during a thunderstorm. You see a flash of lightning. 8 seconds later, you hear the crack of the thunder. How far away did the lightning strike? Two different wave speeds are happening. We got the speed of light because technically when the lightning hits, we don't see it instantly. We see it, the light has to travel to our eyeballs. And then, of course, there's the speed of sound we got to worry about. But if we do the math for the speed of light, we have a distance of 1,610 meters. And this is just from an example, like let's say it's a mile away. So it's just saying, hey, if it was a mile away, it would take the light 5 microseconds to get there. We can't tell the difference between a microsecond, so it's essentially instantaneously. So we just pretend, maybe not. So let's look at the sound. So we'll assume that the speed of sound has this room temperature value of 343 meters per second. That was given in your book. It's just like a general, hey, that's what it looks like. That's on page 482. It gives the speed of a couple different things. During the time between seeing the flash and hearing the thunder, assuming we see the flash instantaneously, which that 5 microseconds might as well be instantaneous, the sound travels this distance. So again, velocity equals distance over time, just rearranging it. Distance equals velocity times delta t. Great. So the velocity was 343 meters per second. The time was 8 seconds. So all we got to do is multiply those two guys together, and we get 2.7 times 10 to the 3 meters. Convert that to kilometers if you want. Doesn't matter. This is fine. 2.7 kilometers. That's pretty far. And that kind of makes sense. So now you happen to know if 8-second delay, then you know it's 2.7 kilometers away. Okay, let's do the next one. 65. Oh, okay. So this is remembering the difference between snapshot and history graphs. So remember a snapshot graph like these? We're taking a picture of what the wave literally looks like at a certain amount of time. So at T1, let's just say at 1 second, this is literally what the wave looks like. At T2, this is what the wave looks like. At T3, this is what it looks like, and at T4, this is what it looks like. If you were taking like a video, this would be frame 1, frame 2, frame 3, frame 4. A history graph is saying, let's pick a single point, in this case x1, arbitrary point. Let's take that point and let's map out what happens to that point over time. So notice these graphs are y and x, but this graph is a y and t. So at t equals 1 second, if this is 0, assume this is 1, what is happening at our point x1? Well, we know this little guy is up just a little bit. Then what's happening at this point during t2? Well, he's all the way up there. And then what's happening at t3? He's kind of back down here. And then what's happening at t4? At t4, at our point x1, our point is on the line. So what ends up happening is the history graph looks almost like a reverse of the snapshot graph. Okay? So this is describing the motion at a single point, and these are the pictures of the wave at different times. I encourage you guys to go back and try to do these example problems right here, these little quick checks. I'm not going to do them here just so you don't have to listen to me talk forever, because we will be here forever if I go through these. I'm going to bring you back to this stuff. So the slides before this spend a bunch of time explaining how the amplitude and the sinusoidal, and we smush them all together and we get these crazy equations where we can get the displacement of a traveling wave moving to the right with regards to the y direction if we know all this information. So if you want to know how far up you are, what y position you have, and you have this information, you just plug it in here and we get it. For example, the amplitude, which is the distance from here to here, or from here to here, it's fine. X, which means how far over to the right we are. Wavelength, which means how far from here to here, or from here to here, or something like from here to here. Those are all wavelengths. We need the time, so however long we were waiting for this to happen. And then we also need the period, so the time it takes for the wave to go from here to here. So you have all that information. We can find out what the x value is on the, what the y value is on the graph. And this is, if it's traveling to the left, the only thing different is this positive or negative. So if it's moving to the right, we use this. If it's moving to the left, we use this. So that brings us to this problem, which is kind of intimidating. But if we sit back and realize all we need to know is understand that that equation that we just looked at has pretty much everything we need to know, we'll be good. And we can find that equation on page 485. It's equation 15.7, and the other one is 15.8. 15.7 and 15.8. So in this question, it says a boat is moving to the right at 5 meters per second with respect to the water. An ocean wave is moving to the left opposite the motion of the boat. The waves have 2 meters between the top of the crest and troughs. The period of the wave is 8.3 seconds. Their wavelength is 110 meters. At one instant, the boat sits on the crest of the wave. 20 seconds later, what is the vertical displacement of the boat? This is throwing so much information at you. If we draw a picture, it'll look something like this. If we write down all of our known stuff, it should look like this. Now, I wouldn't write this. This gives me anxiety. I would write them in little categories, but to each their own. So we know that with regards to the x position, the boat starts at 0. That's what the question was given. It's like, we start at the crest of a wave. Let's make that our 0. It told us that the distance from the high point to the low point is 2 meters, which means the distance from the middle to the top has to be 1 meter, right? So we do have the amplitude. This is probably the most unclear part. If you're like me thinking about this, the boat's moving to the right at 20 meters per second, but it's not on flat ground, right? Like, it's not flat, so how do we know how far it goes? And the trick to this is it doesn't matter what the wave is doing. The boat is still going 20 meters per second to the right with regard to this problem. So you can pretend like this boat is just going 5 meters per second to the right for 20 seconds. Which means we can use the easy equation, velocity equals distance over time. rearrange it to where it's a velocity times time equals distance. And doing that, we get 5 times 20, that's 100 meters. Easy. So we know that the boat is going 5 meters per second. It's doing that for 20 seconds. And in that time, it travels a total of 100 meters. Excuse me. Knowing all of this, we can throw all of this junk into one of our equations. Notice this is the one with the positive because the wave is going to the left. So we throw all this junk into this equation and we can get how high up or how far down you are in this boat. 1 meter is the amplitude from here to here. X is the distance we traveled, which we know is going to be 100. 110 is the wavelength from here to here. You were given that in the problem. The period is 8.3 seconds. You were also given that in the problem. The time it takes is going to be that 20 seconds, right? Because we were in the boat for 20 seconds, so we plug in that there and that there. Let your calculator do all the heavy lifting. We get negative 4.2 meters. So what that means is the boat is actually going to be not underwater, but under the water line, if that makes sense, like down here or down here. And we did all that work for that. And this brings us to this equation, this next thing, the fundamental relationships for sinusoidal wave. Velocity equals wavelength times frequency. Atif knows this equation from chemistry, and Danae and Randy, you've taken chemistry as well, so hopefully you guys remember that also. This is an equation I would expect you guys to memorize, mostly because it's like memorizing pi, right? None of you guys really take any of your brain space to memorize pi. Instead, it's just a thing you know. Pi is 3.14. You don't have to really spend a lot of time to try to think about that. And you should smush this equation in your brain so much that this relationship is just as simple as remembering what pi is, or remembering that you know, what you do to one side of the equation, you have to do the other. Like this is just one of those math concepts, one of those physics and math concepts that you should just solidify in your brain and keep them there. Because in order to do these next couple problems, we will need that. So going over something like this, we did this problem. We want to take a picture of this baby. We know that we have to use that equation. To make a sufficiently detailed ultrasound image, a physician has decided a wavelength of 5 millimeters is required. What frequency is required? Well, if you don't have that equation stuck in your head, you have no idea how to even approach this question. But with that equation, we know we relate frequency, wavelength, and speed. It gives us wavelength. The book itself gives us the speed. The speed of sound through body is 1,540 meters per second. So your brain hopefully is just filling in the blank. Oh, that's easy. We just need to find out what frequency is. We have two of the variables. We just need to rearrange the equation and solve for frequency. So 1540 divided by 0.5 times 10 to the negative 3 gets us 3.1 times 10 to the 6 hertz. That is hopefully pretty straightforward. Let's look at this problem. So all this stuff is part of the electromagnetic spectrum, including visible light over here. So ultraviolet, infrared, X-rays, microwaves, and radio waves, those are all the same type of thing. It's just when it happens to fall in between these wavelengths, our eyeballs are able to pick it up as a color. So infrared light is the same thing, it's just our eyeballs can't pick it up. We can make devices to pick it up, but we can't. So if we get something like this, the wavelength of microwaves in a microwave oven is 12 centimeters. What's the frequency of the waves? Again, if you don't have that equation in your head, equation 1510 on page 486, 1510 on page 486, then you have no idea where to go because you have a wavelength and that's it. Well, you have to remember, okay, well, what's the speed of a microwave? Well, the speed of light is 3.0 times 10 to the 8th, pretty much everywhere. So we have speed as a given thing that just exists. We have the wavelength in the problem. So now we need to find the frequency. And again, it's the same equation, just rearranged. Plug in all your stuff, let your calculator do the work, and you get 2.5 times 10 to the 9th. And that makes sense because microwaves should be, they're all the way down here, so like their wavelength and the frequency is super high, their wavelength is 0.03, so that kind of matches up with what we had with 12 centimeters. And then the next problem, 126. The intensity of light is the amount of power divided by the area. So if you know the power going through a specific area at a certain time, you can find the intensity. So that's watts per meters per second. In a problem like this, we know that a laser is emitting 1 milliwatt of light into a beam that is 1 millimeter in diameter. So the power of the power of the laser divided by the area of the laser, area of a circle being pi r squared. Plug that all in, and we get 1,300 watts per meters squared. And this is just checking to make sure that makes sense. It's roughly equal to the intensity of sunlight at noon on a summer day. That's not really going to kill you, but you know you don't want that in your eyeball, so don't point lasers in your eyes. This last thing, we're going to power through Doppler effect and shock waves. Because we did talk about this, but this was like one of the last days, and I'm pretty sure, Randy, you didn't even mean to be at school. You were there because you had to or something. So I'm sure you all paid attention, but we got to go through it. Doppler effect is a change in frequency due to the motion of the source. We hear that as, if it's sound waves, we hear that as a change in pitch. If you go faster than the speed of sound in air, then you will create what is a shock wave. So when you see like jets and stuff do that, they break the sound barrier. They're going faster than waves can go through air, which is why you get that crazy, all the waves now just build up on one gigantic wave, and that's why it sounds like that crack noise. And that's exactly what a whip is as well. So if we were at school, I would have Austin bring his whip, because of course he has one, and we would try practicing that in the in the morning when no one else was there, because I think a whip might count as a weapon. So I'm not sure if he was allowed to bring that, but whatever, we'll do it. So in this case, let's say a sound wave is a source of a sound is moving towards someone named Nancy, and this is Pablo. So Pablo threw a speaker at Nancy, and this thing is moving over there. As he does that, the speaker is releasing waves, right, at every point. Well, the fact that it's moving, like at this red point, doesn't change the fact that all of the wave will leave from this as a circle. That's what this red wave is, right? And then one second later, when it's at this green position, it lets out a wave in a circle. And then at 2, it lets out a wave in a circle. And what happens is over here, you see that the distance between each of these crests of the wave is pretty big. But the distance here is actually pretty small. So Nancy over here is detecting that whatever song that's playing to this speaker is actually slightly higher pitched. And this guy is hearing slightly lower pitch of the song. And the faster he's throwing this, the more pronounced that is. If he's throwing this at like 100 miles an hour, then it's going to really make a difference, and Nancy probably is going to want to move. But if you're just like tossing it, you probably won't really notice it that much. Oh, jeez. You can hear
Bungee. Piper. Haha. Ready for this? Step.
You'll hear the Doppler effect. Damn it! Sorry. So when he jumps off, it sounds like it goes out of tune, and that's because of this right here. And when he's flying back up, it sounds a little higher pitched because. I hope you can hear that. I don't know. Like I said, this is the test video, so you might have heard double, and it sounds really bad. Here's the equation for that. If something is approaching, if the source is approaching, then the frequency of the source, like the actual frequency, divided by 1 minus the ratio of the speed of the waves under the speed of the source of the waves, equals your new frequency. So this is the speed of the source. So if you're throwing something at 30 miles an hour, the 30 miles an hour goes in the top. Speed of the waves is however fast waves travel normally through whatever you're throwing it through. Okay? So like the speed of sound right here. And then this would be the speed of whatever you're throwing. This is the frequency of the thing actually, like of the speaker. Whatever the speaker is trying to make, this is what the number is, and this is what you will hear if it's approaching you. This is the same thing, it's just, notice this is a positive sign. And this is for a receding source. So if this thing is going away from you, this is what you hear. Pause the video, read this question, and then do it. So it's paused, it's paused. Here's your answer. Police siren has a frequency of 550 hertz. Police car approaches you 450 hertz after it has passed you and is moving away. How fast are the police traveling? Well, let's plug in everything we got. We know the frequency that it's playing. We know the frequency it has passed, right? So it's approaching you at 550, and as it's leaving, it's 450. So we have this value, and we have this value. And we actually do know the speed of sound. Oh, we gotta check. See, I forget my equations already. Speed of the waves is that v right there. So we do have this number right here. So what they do is they subtract the second equation from the first equation. And we get this. So what they did is they rearranged the equations. Notice that Fs is over here now. In the actual equation, Fs is on top, right? So we rearranged the equations, and now we subtracted them, so Fs and Fs subtracted would be 0. We distribute all this stuff, and we can distribute all this stuff, and we get F minus minus F plus plus Vs over V, multiplied by all that stuff. And we see that this right here is going to be in there, and this right there is going to be right there. So that's how we get this. So if we just solve for Vs based off of this equation, solve for Vs, we get this, 100 divided by 1,000 multiplied by 343 equals 34 meters per second, so going 75 miles an hour. We must be on the freeway just as this cop car is driving really fast. This equation is for if approaching observers. So if the sound is standing still and you are moving, this is the equation used. And if the sound is standing still and you're going away from it, this is the equation. Pretty similar, but just a little different. And you'll notice this is just the rearranged versions that the book made right here. Light does this as well. If a light source is moving away from you, it actually is a little bit more red than it should be. And if a light source is moving a little closer to you, it actually looks a little more blue than it should be. And not enough that we can tell with our eyes, but enough to where our equipment, our science equipment, can actually tell. More example problems. Shock waves. As I said, if we're going faster than the waves, all these waves add up into one gigantic shock wave. That's why it's called that. Each wave lines up perfectly, and then this is what we hear because they all just line up trying to go as fast as they can, but not quite. This is what it looks like in air. it actually like bends light a little bit. This is what it looks like in water. So you guys have actually seen a sonic boom in water pretty often. It's just if a boat goes fast enough. Your hand can do this in water. So I don't want to say it's not special, but it's kind of unique thinking that this is breaking this is the equivalent of a sonic boom just in water. This is what it looks like in air. And that's about it. Let's do this. This video is 30 minutes long, but if you think about it in class, that's less than a class. So I know it might seem like you just spent a lot of time, but that's less time than we would spend normally in class. And we went over a whole chapter. I have about 1, 2, 3, 4, 5, 6, 7, 8, like 8 or 9 more videos to make today, which I probably won't be able to do. And my voice is already tired. This is going to be an interesting couple weeks, guys. But you were the first group to see what the video was like, so they will only get better. Hopefully as time goes on. Maybe a little less boring. Maybe I'll play music. Who knows? Do your homework.